Right now, it's my distinct honor to introduce my former boss, Dr. Sarah Jane Leslie, who is a PhD from Princeton in 2007 and is a cognitive scientist who is currently appointed as the class of 1943 professor of philosophy and statistics and machine learning at Princeton University. She is the co-director of Princeton's Natural and Artificial Minds Initiative and is also affiliated faculty in Princeton's AI Lab, the Department of Psychology, the Program of Cognitive Science, Program in Linguistics, and various other centers and programs. And Dr. Leslie is going to be speaking on a topic today that is not at all in the news at all, artificial intelligence and accessible introduction. Please welcome Dr. Sarah Jane Leslie.
All right, thanks so much, James, and thanks so much to everyone for coming out. So we have two sessions. We have a session today and a session tomorrow, and I think a subtly different room, perhaps the one next door. So 1.5 to 2 hour sessions it's not enough for me to get all the way to everything about state-of-the-art AI, as you might expect. But I promise you, actually, if you stick with me through today and tomorrow, you'll come away actually with about 80% knowledge of how these things work. Really all of the core of it, all of the meat of it, both how the predictions, the inferences are made, how the text is generated, and also what the fundamentals are of the training process that lead to that. So today we're going to do the prediction side, so taking some kind of input and giving some kind of output. I'm just going to say, let's just take for granted that the model is, say, already trained. And then what we're going to do tomorrow is turn that on its head and say, how do we actually train such a model? And we actually often talk about this as there being a forward pass of the model. So that's what we're going to do today, from input to output. And then in ways that I think you'll see tomorrow, we often call the training process the backward pass, where we sort of run backwards from a prediction and make little adjustments along the way, which is really the heart of training modern AI. But to start with something even more fundamental, so okay, we're just going to play a game. I am driving in my, I took my dog for a, right, someone said run, right? Most of you said, great, perfect. Most of you said run. I think maybe one, maybe two people said, most of you said walk. Maybe one or two people said run. Maybe I could have said checkup, like I took my dog for a checkup. That's, it's maybe not exactly what you were expecting, but, it's not too bad. I took my dog for an aardvark. What? Like, what is she talking about? As humans, as speakers of the English language, you actually have internalized in your brains expectations about what words might come next. And actually, there's some evidence that your brains, as I speak, are predicting what the next words that I utter might be. So you actually all have, you might not be able to fully articulate it, but when you reflect on it, right, there are some completions of a sentence that are extremely unsurprising. And then other ones that would be really quite surprising, like I took my dog for an aardvark. What is this lady talking about? You can sort of think about graphing this, like how surprising are these different completions, right? Aardvark, very surprising. Banana would be surprising. Check up and run. Walk, extremely unsurprising, right? It's like, could we be more banal? Took my dog for a walk. It's worth noting, like, I took my dog for a runs. That's bad, right? I mean, it's only just one letter difference that would make that actually a very surprising next word, an ungrammatical next word, right? Just that one letter difference makes, makes it something unsurprising into something quite surprising. So if you kind of reflect on that, right, so what goes into this process of being able to predict what words come next? Well, there's a lot of world knowledge, right? Like, what do you do with dogs? Will you walk them? So you have dogs, you walk them. If you have like maybe a Dalmatian, like one of those super energetic dogs, maybe you have to run it too, right? Sometimes you have to take your dog for a checkup. That's something that happens. World knowledge goes into this, right? Also, grammatical knowledge goes into this. I took my dog for a walk, but not I took my dog for a walks. That would be weird. Grammatical knowledge goes into this. Knowledge about meaning goes into this, right? You know, I can say it's weird to say I took my dog for a banana, but it's not weird if I say I took my daughter for an ice cream, right? This sort of, these different meanings, these idioms, the semantic patterns, right? All of this knowledge actually is necessary for you to make really good predictions about what the next word in a sentence might be. This is the fundamental idea behind language modeling, which is itself the fundamental idea behind modern AI. Okay? So we're talking about how surprising things are. So surprise is sort of dual to how likely things are, right? Very likely things are very unsurprising, and very unlikely things are very surprising. So we could have flipped this around and talked about the probability of particular words, right? Aardvark, banana, runs have low probability. Walk maybe has the highest. These two have sort of intermediate, right? If I'm able to make good predictions about what the next word might be, that means that I have internalized a good, sensible, meaningful probability distribution over all those myriad possible words that might come next in the sentence. This is fundamentally what modern AI is trained to do. It's the fundamental idea behind technologies such as ChatGPT, Claude, and the like. We're going to train something called a neural network to take in sequences of words, so maybe prompts, for example, the kinds of questions you ask these machines, and output excellent predictions about what the next word should be. Excellent predictions about what the first word of the response should be, then given that what should be the second word, what should be the third word, and so on and so forth until you hit a point where you predict that actually, you know what, I'm done. No more words come next. Where a prediction here we're going to specifically define to be a probability distribution over the entire vocabulary of the language. Okay? This is the fundamental idea behind language modeling. We are going to come back to this at the end of tomorrow's lecture. Okay? For now, what we're going to focus on is this idea of a neural network, because this is really the engine that drives it. Language modeling is a particular objective that we can train a model on. And you have to do some things that are a little bit fancier, a little bit trickier than the base models that I'm going to show you today. But they're pretty small adjustments. Everything I'm going to show you is the beating heart of this technology. Okay? So let's talk about a simpler task, though it's not by any means a trivial task. What about the task of identifying handwritten digits? This is simpler, but in the 90s, this was actually an incredibly difficult, unsolved task. This was actually one of the first triumphs of neural net technology, broadly construed, was to actually be able to successfully identify handwritten digits, classify them as 0 through 9 in a way that was accurate to what humans intended. So here's a handwritten digit. It's pretty, these are actually quite small images. They're 28 by 28 pixels, which is why when I blow them up, they look chunky. They look like images from the 80s. I think probably, in fact, they are images from the 80s, which is why they look like this. What's an image to a computer? Okay, so this is something that's rendered for you so that you can see it, you humans taking this in through your, your rods and cones on your retina. It looks like something to you, but what is it to the computer? So in fact, an image to a computer is a rectangle filled with numbers. And we just render these numbers in different ways. Here I've rendered the zeros as white, and I have rendered the higher numbers as black, and then intermediate numbers are kind of gray in between. I could have easily inverted it. Incredibly easy to invert this. These numbers are actually what it is to the computer. Okay? So I can take away the 5 that's superimposed there. This is really you can still kind of make out the 5 actually. It's a sort of little wiggle as you see the higher numbers, the ones that I mapped in a moment ago to darker values. You can see them kind of rendered here. Okay? So this is the sort of thing that the computer has to work with if we ask it to identify handwritten digits. In fact, what I'm going to do is something a little bit weird. And the reason I'm going to do this is that what I'm going to show you in a moment is really the simplest, most basic case possible. If we want to be a bit more sophisticated, we could probably skirt this step, but we're not going to get into that here. Here's what I'm going to do. I'm going to take this square of numbers, and I'm going to make it instead one long list of numbers. Okay? I'm just going to flatten it out. I'm going to take that top row of a lot of zeros, 28 zeros, and fill those in. Then I'm going to take the next row. I think it's another 28 zeros. Enter those next. And then the next row, and so on. 28 by 28, I'm going to end up having 784 numbers, because that's 28 times 28. Here's a little subsection. Where did these numbers come from? They're actually from the picture here, 3, 18, 18, 126, 136, and so on and so forth, right? I just flattened it out. I had a square, and now I have a line. Think about it like beads almost, sort of taking them off a square and then just placing them next to each other. I'm going to do that. Get a list of numbers. We can call it a vector if we want to be fancy, but we don't have to do that if we don't want to. And what I'm going to do is for each image, the input into the neural net that I'm going to actually train for you in a moment is going to be a list of numbers, specifically a list of 784 numbers that came from the original handwritten digit. I'm going to have a whole lot of them, 60,000 to be exact. And I'm going to have labels. So this is important. I'm going to train the model. The approach that I'm going to take, so old school AI was a lot about humans taking the input and thinking really, really hard about what rules might help you get from input to output. So like maybe I would reflect on, I don't know, the fact that, you know, okay, if this is a 9, right, I've got kind of a circle here and a line down here. Maybe I try to think of clever ways to get from pixel values to features like that. Maybe I say, okay, when it's like this, it's a 9. But I don't know. I mean, like if you have something that's probably still a 9, at some point it becomes maybe like a weird 4, right? What exactly is the line that we draw here? I mean, maybe if you think really hard about it, you can get somewhere. In fact, pretty much people didn't. People tried doing that, and it's very limited how far you can get by reflecting yourself as a human and trying to come up with rules. Modern AI, modern machine learning inverts that paradigm, and it says, here's what I'm going to do. I'm going to give the machine inputs, and I'm going to give it correct answers, and I'm going to let the machine, in a clever way, figure out what the rules are to get from the inputs to the outputs. So critically, I'm not only going to give it this kind of weird flattened image, but I'm also going to give my machine, but by the machine, it's actually literally going to be my laptop, and I'm going to give it true labels. So if here were some inputs, the true label for this column would be a 0, these would be a 1, and so on and so forth in what is hopefully a pretty obvious way. Okay. And I'm going to train it on 60,000 such examples. Okay. So I guess, right, it's going to be my input. It's going to see 60,000 flattened images and their true labels. I'm going to have another 10,000 that I'm going to hold back, because that's going to let me test how well my model's doing. You know, it's a little bit like how you might give your students a practice midterm, but then you want to have a real midterm that's different than the practice midterm so that they can't just like memorize the practice midterm. So that's going to let me evaluate how well my model's doing. All right. And what is my training objective going to be? What I'm about to ask my laptop to do is learn how, when given an input, a string of numbers, 784 numbers, I'm going to ask my laptop, train my laptop, to output a probability distribution over these 10 possibilities. 10, because it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible categories. I want a probability distribution over these. One that assigns as high a probability as possible to the correct answer, and correspondingly low probabilities to everything else. Put differently, we want the right answer to be as unsurprising as possible. We want it to be banal. We want it to be boring, like, yes, I knew exactly that that was what was going to happen, okay? A little bit. All right, so let's just confirm these are the digits that we're talking about. Yes, they are. This is the kind of thing we see in the input before it's flattened out. And I'm just going to do is I'm going to flatten out the images. I'm going to build a model here. So something weird that I'm doing, x equals layers.dense 512, activation equals ReLU applied to the inputs, outputs are layers.dense 10, activation equals softmax of x. You're going to understand all of that by the time I'm done with you. For now, it's, hocus pocus, abracadabra, no problem with that. Model.compile. Now, okay, at this point, what my laptop has done has created a model of the sort of shape that I just told it to create. And just looking ahead a step, what's really at the heart of all of that are what we're going to call weights and biases. And right now, these weights and biases are random numbers. So actually, at this point, I can give my computer some of these images, these flattened out, unrolled images, and I can ask it to predict which category it belongs to. A 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It hasn't been trained yet, but shall we see what it does? Let's see. Here is some. Okay, here, this one it thinks is a 1. This one it thinks is a 9, a 4, a 1, a 4. We got that one right. Actually, right, if you're guessing at random, you're probably going to get 1 out of 10 correct, right? 4, a 4, all right, again. All right, pretty terrible predictions. We can actually see on our whole test set, let's see how well we do overall. This number here, 10.65, that's the percent that it got correct on the test set. No surprise, because it's guessing at random, right? It's like you have a multiple choice test with 4 possibilities. The student who selects all C's is going to get 25%, right? That's basically what it's doing. And now what I'm going to do, in a moment, I'm going to press this button. And the laptop is going to take those 60,000 training examples. It's going to make terrible predictions about them. And then it's going to ask, how could I do a little better next time? And it's going to change those weights and biases that I mentioned along the way in a whatever direction would make the prediction a little bit better next time. Then it's going to do that again, make predictions a little bit better, and ask, how can I improve? And it's going to do this a bunch of times. And it's going to do this unbelievably fast, which is why I haven't even pressed the button yet. Should we do it? Shall we unleash it? Training. This is just my laptop, nothing fancy about it. Get these little arrows. It's doing something. What is it doing? And I think it's over. Shall we see? We were at 10.65% last time, right? Let's look at some images first. Okay, prediction is 7, 2, 1, 0, 4, 1, 4, 9. Wow. 5, this one's kind of hard, right? 9, 0, 6. And these P's here, these are the probabilities that it's assigning to these categories, okay? And this one here is kind of nice. Look at it. These are mostly, it says like, 1 or arbitrarily close to 1, right? 0.72 that it's a 5. I mean, would you be 100% confident that that one's a 5, right? It's probably a 5. I think it is a 5. The machine's kind of uncertain of this too, right? It's kind of sensible. Should we see how it did if we actually put a number on this? Let's see. And now our accuracy on the test set, the ones it didn't see before, is now over 98%. From just those like 30 seconds of training, we went from guessing at random to an almost perfect score. How? how did we do this? So as I say, tomorrow we're going to talk about training. Today we're going to just talk about and we can think about it whether making predictions now after training, like at the end, or we can even think about it as far as how it makes predictions with those random weights and biases that I keep mentioning, right? It's the same exact process, this forward pass. Give me an input, I run it forward, I make a prediction. That is, I come up with a probability distribution over the numbers 0 through 9. Here's a schematic rendering of the model that we just trained together. Up here is saying, and in fact, I think I could only fit like 16 or something on the slide, but if I showed you the whole thing, there would be 784 circles in that top row. 784, that's 28 by 28, right? When I have this square, and then I unroll it into one long thing. 28 times 28, 784. 784 numbers constitute the input every time. Why? Because that's sort of the images that I'm dealing with. That was how I process my data. This is what I'm giving to the model, okay? 512 units in the hidden layer. What is that? Very mysterious. So 512 is actually a number. I just picked that number. I mean, not at random, because it's not my first time doing this, but that's actually a number that's up to the coder. I could have done 500 there, and it wouldn't have made any difference. 512, because people in this world like to use powers of 2, and 512 is, I guess, 2 to the 9th. So that's why I picked that one. It's maybe not as arbitrary as it seems, but there's some flexibility there. Then at the bottom here, 10 circles, 10 output units. Why? Because there are 10 possible outcomes, right? 10 things that I want a probability distribution over, digits 0 through 9. All right, so these are numbers. Ultimately, we want this to be a probability distribution. How do we get there? So this mysterious hidden 512 hidden units. So each of these is going to represent a weighted sum of each of these 784 pixel values, numbers in the input. There's a little star because there's a little complication that we'll come back to. And each unit in the output layer is going to be a weighted sum of these 512 hidden units. What do I mean by a weighted sum? So if you're a student, or if you're a professor, or you're in any way involved in the education world, you're probably extremely used, in fact, everyone's used to weighted sums. I know that students understand weighted sums, because if they didn't, I could calculate their final grades however I wanted, and they wouldn't be able to complain about it. And in fact, they do. So hidden sums, I think, is something weighted sums is something everyone's familiar with, all right? So final grade calculation, if I'm teaching and I say, okay, final exam is worth 50%, 30% midterm, 20% homework, right? This is boring, right? Like here's student 1, got these grades, and I just calculate student 1's final grade like this, right? 0.5 times the grade on the final, 0.3 times the grade on the midterm, 0.2 times the grade on the homework. Turns out it's 89.1 here. I mean, I just made up these numbers, right? Student 2, same thing, different inputs, right? Different inputs, same weights. Why? Because if you weight one student's grades differently than another, then you're being a very bad professor and everyone gets to complain about you, right? Same weights, but different inputs each time, right? Which results in different outputs. And I could, at the beginning of the semester, probably not halfway through, but at the beginning of the semester, I could decide instead to weight these differently, right? I could have done 30, 30, 40, more emphasis on the homework, right? Student 1's grades are the same, but now they went from an 89 to a 91, right? So this should be so boring, right? Just super boring and easy. This student, I think, also went up this way. People do better on homeworks than exams, right? Weighted sums are how we calculate final grades. They're also how you calculate take-home pay, right? If you have, suppose you're a student working 3 jobs around campus, and say, I don't know, the library, the dining hall, the coffee place, or something like that. And there you work different numbers of hours at these 3 different jobs, and you have different hourly rates for these 3 jobs. You want to figure out what your take-home paycheck should be. Make sure Princeton's not stiffing you, right? Again, you know how to do this, right? It's a weighted sum. You weight your hours by your hourly rate, and multiply those pairs of numbers together and add them up, and that gives you your take-home pay. Suppose the student also gets a fellowship stipend, so that's just some amount which doesn't actually depend on hours worked, right? So you can also make sense of adding into these weighted sums a quantity that is actually independent of the inputs, independent of here the hours worked. So let's do that. We know how to do this, right? You just add, like if you get $1,000 on top of that, you just add it, right? I mean, this is supposed to be unbelievably basic because I want to convince you all you actually understand almost everything about how even modern AI works. If you understand this, you're like almost there. I just have to convince you of that. You can have a new rate for your hourly pay rates might change. Your fellowship stipend might change. Your, these weights and this term, this bias term might change, right? And we can calculate what the new paycheck is. It went up, very nice, right? Weighted sums, multiplying pairs of numbers together, and then add some other number at the end that's independent of the inputs. I'm going to refer to these as the weights. Here, the weights correspond to how much weight, as far as your paycheck, does each hour at each job correspond to. And I'm going to call these biases. Doesn't mean bias in any kind of social bias sense. It just means it's a technical term for a number that does not depend on the input. Okay? If you remember, like, high school algebra, equations for lines, like y equals mx plus b, right? M, the slope multiplies it gives you it multiplies x and it tells you the slope of the line. And then b, the y-intercept, right? So that like slope goes like this, y-intercept is like that, right? Yes, my interpretive dance of 8th grade algebra. Right, so just pretty like familiar concepts, hopefully. Notice that, I gave you 2 weighted sums here. I could have kept going, right? I could have just said, okay, let's consider another bunch of hourly rates and other biases. I could have done it 3 times. I could have done it 4 times, 5 times. I could have done it 512 times if I'd wanted to. By that point, you'd probably be walking out on me, but I certainly could, right? All I do is I come up with, anytime I have different weights and a different bias, that's going to give me, for any given input, a different weighted sum. Do it once, twice, 5 times, 512 times, as many times as you choose. You just need to have a weight for every element in the input, and every element in the input needs to have a weight. So you can't, there has to be a pay rate for every job. That pay rate could be 0. That would be, sociologically terrible, but mathematically fine, right? Or you might work 0 hours at a job. No problem with zeros, but you do need, for a weighted sum, to be able to pair up these numbers. Okay? So what does this mean? Okay, so now let's make it more concrete. When I said that this hidden layer consisted of 512 weighted sums of the input, what this meant was, for this first circle, I had one weight for this first pixel value, and another weight for this second pixel value, and a weight for the third one, and the fourth one, and so on 784 times. And that was for this first element in the hidden layer, and I have that 512 times. So that means they're actually associated here 512 times 784, which turns out to be, right, and then I also want to, I give myself the freedom to add a bias term, right, a term that doesn't depend on the input. And I'm going to let each of these 512 weighted sums have its own bias term. So I have this amount of weights to learn, and I have 512 bias terms to learn. So in total, I have a little over 400,000 things to learn, numbers to learn, parameters to train. That's what my laptop was doing just now. And then how do I get from this layer to here? So for my output, I have 512 inputs now. Kind of the hidden layer sort of serves like the input now to the output layer. And I have one weighted sum of these 512 plus a bias term, another weighted sum of these 512 terms plus a bias term, and so on. I have 10 of them, one for each of my outputs, plus 10 biases. It's not yet a probability distribution. We're just like filling in little pieces as we go, okay? But altogether, this gives us a bit over 400,000 parameters, which are the collective term for weights and biases, which is what my laptop just learned. It learned really, really good values of these that got it 98% accuracy. I haven't told you how. Let's just make this forward pass a little more concrete. Let's just switch to a simpler model for now. So suppose I'm trying to predict the price of houses. Okay, suppose I'm trying to take some measurements about houses. This is probably not going to compete with Zillow. Suppose I measured the square footage, the number of bedrooms, the number of bathrooms, and then the acreage, like the size of the lot that the house sits on. What I want to do is predict the price of a house based on these 4 input features. Okay, I'm not saying this is going to be the best model ever, but let's simplify it to make this all as concrete as possible. Okay, so I have 4 input features, and I've determined, and again, it's always the coder's choice how many units to have in the hidden layer. Or sometimes you might even have more than one hidden layer. That's up to the coder. Students always want to know, how do I know what a good answer is there? And the truth is, a lot of it comes from trial and error and previous people's experience with these sorts of things. 5 would be a pretty weird choice here, but I don't want to overpopulate the slide. So let's just go with this. So I have 4 input features, and I decided I want to have 5 units in my hidden layer. That means I want to have 5 weighted sums of 4 input features, okay? These 5 weighted sums, and I'm going to add 5 bias terms, 1 for each of the weighted sums, just so I have a little flexibility, a little additional flexibility to put something in there that doesn't depend on the input. The value for these hidden layers are up to a little complication given by the weighted sums of these inputs plus the bias term. And then my output down, well, I guess I'll come back to the output. So let's just look at this in even more detail. I kind of blew this up and I color coded it, right? So let's look at this first hidden layer sum. So let's just adopt, right? So I put like W11, 12, 13, 14. These, right? This is the weight, this W11, the weight that for this weighted sum we're going to attach to square footage. Here's the weight that for this weighted sum I'm going to attach to bedrooms, bathrooms, and acreage. 4 different numbers independent of each other. And I can add my bias term. So I'm computing this number here is just W11 times whatever the square footage is for a particular house, plus W21 times the number of bedrooms, 3-1, bathrooms 4, and then the bias term at the end. Again, if you want to think about it like these numbers are just random numbers, like thinking about the outset of it, that's great. Or you can think about these numbers, these weights and biases as like, we've already trained the model, haven't told you how yet, but I will, okay? So some numbers or others, right? And the same for all of these other hidden layer terms, right? They each have their own set of weights. Each of these 5 has a set of 4 weights plus a bias term. Here's the ones written like this if we want. If you are familiar with matrices, you can write it like this. It really doesn't matter. You don't need to think about it in matrix format if you don't like that. And then we have our bias terms for each. Here's B1, the bias term for this hidden sum, and figures there in the equation. Okay. And then how do we get to the output from here? We want to take 5 numbers and transform it into 1 number. We just need one weighted sum. Here I only have one thing. I'm only outputting one number here, which is going to be the predicted price of the house. Okay? So I have these 5 units in the hidden layer. So I need to give each of them their own weight. So I need 5 weights. Then I always allow myself a bias term just to give a little additional flexibility. So what I do is I have 5 weights and 1 bias term. And the output here in this case would just be that weighted sum. This example is kind of nice because we don't need to worry about probabilities just yet. We'll come back to them. So if I really made a lot of observations about houses, and I had the prices that these houses actually sold for, I could just as easily as I did with handwritten digits, train a model to make these predictions. How good the predictions would be would depend very much on whether this information is sufficient to make a good prediction about the price of a house. And realistically, it's probably not, right? Like you need to know a lot more about a house. But that's more of a sort of data issue here, right? We could train a model to make a prediction like this, right? We can think about it graphically. This is what the little weights and the biases are attaching here. And here's the equation, if you like, for the output, just a weighted sum. Here are the weights, the black weights, of each of these hidden units, which are themselves hidden weighted sums with a complication I got to come back to. All right? So machine learning, as I've been saying now for a little while, consists in letting the machine learn really good values for these weights and biases. And this is what we're going to go into depth on, how that happens next time. So for this little tiny model, if you add up all these weights and biases, turns out there's like 31 of them. So a lot less than the 400,000 that we had for handwritten digits, but this is just a toy model that I can kind of fit nicely on a PowerPoint slide. What would happen if we just went straight from the input to the output? Like if I just took these 4 input features and did a weighted sum of them directly and used that as a prediction of price. This would mean I had 5 parameters in my model, right? So 4 weights, 1 each for these 4 input features, like square footage, bathrooms, bedrooms, lot size, right? Plus a bias term. This direct model is only 5 parameters, very simple. It's also known as linear regression. Is anyone familiar with linear regression in the room? A few people, a little bit. Linear regression really just means let me make a prediction based on a linear model that is a line, that is, and how I get to, like, you know, do my interpretive dance again, right? So I'm just going to find some way of weighting the data plus, you know, give some kind of bias term in there, some kind of linear, some kind of straight line model of the data. So sometimes that works really well, and sometimes it works not at all. It wouldn't work for handwritten digits. It would maybe be okay enough for house prices, I don't know. It's linear regression. It's been around for a very long time. It's not what we would probably call modern AI. So, but here's a complication. So everything I've told you thus far, if anyone was very astute in the audience, you might have noticed this, is that actually Okay, here's a problem, is that a weighted sum of weighted sums is always just equivalent to a single weighted sum, okay? So actually what I've suggested to you so far about hidden layers, they're actually totally useless. Oops, is modern AI based on a lie? Why is this? So here's a weighted sum. X and Y are just whatever these input features might be. All right, so here's one weighted sum with a bias term, 3 times x plus 4y plus 1, 2x plus 5y plus 2. Two weighted sums, and here's a weighted sum of those two weighted sums. Let me do a little bit of elementary algebra, multiply everything out, collect the terms. Here's a weighted sum of x and y in its own right. Oops. Multiplication and addition are linear operations, and concatenating them together never gets you outside of linear land, right? So I can go like this, I can do all that. What I can't do is bend like that, right? I can never do that if I only have multiplication and addition. So it looks like, these hidden layers might be useless. What can we do? Okay, and you can kind of do the algebra here. If you took me literally at my word without, there was actually an asterisk in there saying another complication, right? So here's the equation as we have it of a very small, I guess this one's only beds and baths. Okay, so this one here is a weighted sum of beds and baths. So that's, 1, 1, 1, 2 times that. This one is a weighted sum of the number of beds and baths. And then, so it gave me two weighted sums, the things in parentheses. And I attach to them some kind of weight. But now let me multiply out, collect my terms. And now whatever this number is, and it's just a number, could be the new weight, and this could be the new weight on baths. And it looks like the whole thing is just equivalent to a linear model, okay? Like this. What we need to do is add in something that is not multiplication or addition. A nonlinearity, something that gets us out of linear land and into some other kind of land. Something that lets us bend and curve and fit our data as needed. This is the one trick. So the original way of introducing nonlinearities in machine learning was actually inspired by neurons in the brain, which you might think of as either firing or not firing. Maybe if they fire, you can model them as emitting a 1. And if they don't fire, if they're just silent, you might model that as emitting a 0. Either send a signal along or they remain silent. So here's an idea. Let's take a number, any number whatsoever, from -infinity to infinity, and let's bend it to be something between 0 and 1. It's actually a very nice function that does this. It's called the sigmoid function. Unless you're a stats person, then it's called the logistic function. So we could apply this function to our weighted sums. And hopefully it's just very obvious, even though I haven't given you the equation for it, that this is not linear, right? We're very far outside of straight line land. Now we're sort of curved and bent to fit between these two numbers, right? So if we had as our weighted sums in our hidden layer, let's say these values, I'm just making these up, turns out if you apply the sigmoid function to them, then what you get are these numbers. So the larger positive numbers get mapped to something very close to 1, and the negative numbers get mapped to something pretty close to 0, okay? In the middle, you get the full range of possible numbers, but for most of the real number line, you are very close to 1 or very close to 0, approximating this idea of firing, boop, 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 or just not firing, remaining silent, 0. So you could think about this if these were actually hidden layer values. It's like these ones are firing, and these two are staying silent. Okay. So nowadays, on hidden layers, we tend not to use this function, though I like to start with it because I think it's kind of easier to build some intuition from it, this idea of firing, boop, 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 or not firing, silent. Instead, we use a function called ReLU. It stands for rectified linear units. It looks like this. So ReLU is a bit of a weird function, but it's extremely effective. What it does is it leaves positive numbers unchanged, and it maps negative numbers directly to 0. Okay? So it sort of retains that spirit of sigmoid by letting a unit either fire or not fire. But you can think about it, instead of firing being a univocal thing, sending a 1 and that's your only option, now you can fire in a multitude of ways, right? You can fire with any positive number, okay? So if we applied ReLU to this set of numbers, we would leave the positive numbers unchanged now as opposed to being mapped to 1. However, these two negative numbers would still be replaced now with 0. Okay. So if we look at it here, we still have this effect where two of the units, the same two, are not firing, as it were. But now you can really think about it like a more expressive version of sigmoid, whereas previously the 3 units that were firing had to fire at exactly the same rate, have the exact same number, and now they have more expressivity in that this one's a 10, whereas this one is just a 5. Okay? So this is a non-linearity. And so if I actually write out really what the equation is for the hidden layer sums here, I want to make sure I put a ReLU in front of them. This one, I compute the weighted sum exactly as I told you before. I didn't lie about any of that part. The only part that I had previously missed out is then I take those weighted sums and I just check, are any of those weighted sums negative? If so, I replace them with 0. If they're positive, I let them stand. And similarly for the remaining other weighted sums. I just do this somewhat strange thing of zeroing out the negative numbers. Why do I do this? Like, what does this gain me? I mean, it certainly gains me that now I am not equivalent to a linear model. Okay, you can't, the algebra I showed you of like multiplying out, collecting the terms, right, all of that, I cannot do that now. ReLU just sits right there blocking it, okay? It just sits there blocking it. So I can't do that trick. That's progress. I'm no longer like showing you something completely useless. I mean, linear regression is far from useless, but it would be nice if we were doing something that wasn't just linear regression, right? So why? What does this really gain us, like, concretely? Okay. So let's take a really simple example. Suppose there are 4 kinds of berries in my environment. The berries can be either pink or purple, and they can be either big or small. Okay. And here's what I'm going to tell you about the berries. If you are small and pink or big and purple, then you are safe to eat and, in fact, delicious. However, if you are small and purple or big and pink, you are poisonous. Uh-oh. All right, I really like my model to be able to detect which berries are safe and which berries are poisonous, okay? So let's kind of plot this, right? So let's just suppose we assign some kind of number for color, like say lower numbers if you're pink and higher numbers if you're purple. It's pretty arbitrary. Right, and I plot my berries. Each of these little splodges is a berry observation, right? Here's a color axis, and here's a size axis, right? That would just sort of measure the size of the berries, right? So here is a fact about linear models. If I want to use a linear model to classify my berries into poisonous and safe, it's linear, it's a line. All it lets me do is draw a straight line across this color size plane, and I can put it here, 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 but there is no place that I can put it that separates the poisonous from the safe, right? just, you don't even need a proof. You can inspect it with your eyes. No straight line can be drawn through this plane that correctly puts the safe ones on one side and the poisonous ones on the other, right? It cannot be done. This is a case where a linear model, a straight line model, cannot cut it. It just doesn't do the job, okay? So a model that goes straight from is just a weighted sum of the color and the size, these two features, it's always going to end up looking like this. If I plot it in 3D, it's going to be something like this. Okay, so here I'm actually, what I was showing you before was just the intersection of this plane with this flat surface with this plane here. Now this is actually what a weight is, right? If y equals mx plus b, I have one variable there, x, right? If I have two variables, like z equals, ax plus by plus c, that's a plane, right? You take a line, go up a dimension, it becomes a plane, a flat surface, right? Like a piece of paper or piece of cardboard, maybe I should say, right? A sheet of glass, a plane, right? Like that. Okay, that's what these equations are equations of. And no amount of multiplication and addition, linear operations, will ever make this sheet of glass bend, right? It will always, you can position it however you want, but it will never bend. It will always cut somehow like this at an angle like this, okay? What happens if we move to a model, a very simplest, smallest possible model that can solve this task? If we give the model the flexibility to have a little bit of non-linearity in it, now we can get something like this. Okay, now we're actually correctly separating poison from safe in an accurate way. I'm not missing out on delicious berries, nor am I risking being poisoned by bad berries, right? A model like this can learn to classify in this way. How? Let's go back up to 3D. It actually learns as a surface like this. Just the introduction, it doesn't have to be totally obvious why this is the case. Just think about it as a binary of like linear versus not linear. Once you're out of linear land, you can bend. You don't have a sheet of glass anymore, you have a sheet of rubber, right? I can bend it, so now it goes up and it comes back down, cutting this plane in two places, right? This nonlinearity, this introduction of ReLU, this is a real surface, by the way, this is a real model, a real plot, a model that my laptop learned. Just introducing a hidden layer that has this nonlinearity on it lets you have, instead of a stiff sheet of glass, something now that can bend and learn more interesting functions. Okay? If you sort of think back to the handwritten digits, right? Is it at all plausible that there's some kind of straight line, as it were, that maps you from the inputs to the outputs? Probably not, right? In fact, not. But just even having that one hidden layer, and with that case, we're in such high dimensions we couldn't begin to graph it, but just that little tweak there allowed my laptop to learn how to classify these digits with 98% accuracy. It could not have done that had I not given it the flexibility to bend in this way. So let's put this together again. So we have our weighted sum, 512 weighted sums of 784 input features. Compute those weighted sums, then apply ReLU. Just replace any negative numbers with zeros. And then take that output of ReLU, these 512 values, and compute 10 weighted sums based off of those to plus bias terms to get something here. Then do what? Kind of wanted probabilities here. We're not there yet. Okay. So what we have now are 10 numbers that are themselves. We haven't applied ReLU or anything to the output. We haven't applied anything to it. We just have now 10 weighted sums. We're in better shape now because our hidden layer gives us the flexibility to learn something bendy. But what we have now are these 10 numbers. We'd really like these to be probabilities. We'd really like these to be 10 numbers that are each between 0 and 1 and which together sum to 1, because then I'll really be able to say, okay, like this is 99% chance to be a 9. And this is, it's probably a 5, but maybe I'm only like 0.74 chance of being a 5 or something, if that was what it said before, right? So what do we do here? So I'm going to call these 10 weighted sums Z, just so I have some way of referring to them. Right. So how do we convert these 10 numbers in Z to a probability distribution? All right. How do we get these 10 numbers that are anywhere? They can be like negative, positive, tiny, large, right? How do we get these to behave themselves so that they add up to 1? And none of them are negative. Well, so maybe there's something like this. These are just like random numbers that I generated, but that's pretty typical. These these weighted sums, these Z values might look something like this, okay? So the first problem I want to address is that some of these are negative. It's very, very bad. You can't have negative probabilities, very much disallowed. So here is a trick. Here's a trick that I'm going to use. We can raise numbers to powers, right? So if you have, you have 10, and then you square 10, you get 100. You cube it, 10 to the third, you get 1,000, right? 10 to the sixth is 1,000,000. I can also take 10 or any number to negative numbers, right? So 10 to the negative 1 is 1 over 10. 10 to the negative 2 is 1 over 100, right? There's a negative in front. I just consider it like 1 over that number. So it's just a trick, right? I can observe that when I take a number to a power, even if that power is negative, it'll never give me a negative number out, right? 1 divided by 10 to the whatever is going to be still a positive number itself, right? 10 to the negative 6th is 1 over 1,000,000, right? That's a very tiny number, but it's still a positive number, okay? So just think about this even as nothing more than a mathematical trick, if you like. Something I can do is take a number and consider these to be the exponent of that number, the power to which I will raise this number. And for this purpose, I'm going to use a special number, E. It's like 2.718, thereabouts. It's a special number. It's kind of like how pi is a special number, one of these like super cool numbers that comes up again and again. Honestly, I could use any number here. It's not really going to make much difference. By convention, we use E because it makes some of the math come out nicer, okay? So I'm going to take this number and I'm going to compute e to the 0.96. So that's going to be super close to e itself because e to the 1, right, is 2.718. But when I take e to the negative 2.81, that's going to be 1 over, close to e to the third. Pretty tiny number, but still positive. What happens if I take these numbers and do this? I get something like this. Here's what's nice about it, right? And sometimes I should say, students sometimes say, well, why not take the absolute value, right? Why not take the absolute value? Remember that, right? That just takes a negative number and replaces it with the corresponding positive number. Here's something we would like, because it's going to make it easier for the model to train, to learn to do these things. We'd like to preserve the relative ordering, okay? So this here, the 4 is the smallest number here. And I guess 6 has the largest number with it. If I took the absolute value of these numbers, 4 would now be, well, maybe it wouldn't replace 6, but it would be, I think, it would be the second highest number. It would go from being the smallest number to the second highest number. This is just, you can just take my word for it, it's a kind of jumpy, jagged change that's going to make training much harder. What's really nice about exponentiating, if you sort of track this relative ordering, right, so 4 is the smallest, 6 is the biggest. On the next slide, this remains the same. 4 is the smallest, and 6 is the biggest. And all the other numbers remain ordered as they were. So this is like why we might think to exponentiate to deal with our negative numbers as opposed to something that may be more immediately called to mind, like taking the absolute value. We'd like to keep this relative ordering. And exponentiating does this, so we like it. One outstanding problem, probabilities have to sum to 1. And these numbers very much do not sum to 1, right? One of them here is actually 18, right? Very, very bad. Definitely not a probability distribution. So we need them. None of them are negative, so that's great. Now we just need these to sum to 1. And we will have something that qualifies as a probability distribution. Fortunately, this problem is very easy to solve. All we do is we are going to sum up all of these numbers. And then we're going to divide each one by that sum, okay? Why? Because then it's just going to add up to be 1, right? If you have numbers that add up to 100 and you divide each one by 100, then they're going to sum up to be 1 now, okay? Cute little trick, works every time. And what we get out is something like this. So notice that 6 is still the biggest, right? Now it's something we can consider a probability, 0.35. 4 is still the lowest. I mean, this is decimal point rounding. It's rounded to 0, but it's going to be something very, very small, not identically 0. And these other ones are also quite small numbers. Whatever this is, 9 remains the sort of biggest competitor to 6 over here, as it was on the previous slide. So we just scaled everything down by dividing through by the sum. And if we wanted to write it all out in a formal mathematical way, that would be what it looks like. This function is called softmax. It's a very useful function. It takes a bunch of numbers anywhere from negative infinity to infinity and turns them into something that can be considered a probability distribution. Okay? Exponentiate, and then sum, and divide through by that sum. So let's explore what this looks like then in the berries case. And we're coming to the end of the new content for today, and then I'm really glad. I should have said you should interrupt me with questions, but we'll certainly have a lot of time at the end for any questions that anyone might have. So let's see what this looks like. So if you remember in the berries case, I was showing you these planes in three-dimensional space. And I mean, one thing you could have called me on is like, what do these numbers correspond to? Like, how do I interpret these planes in three-dimensional space? I'm going with the flow, but I don't really know what to do with them, right? So we had this. Here's our good model, right? And what I showed you in 3D was something like this. Okay, so this one, the graph gave out at like -15. What does that mean? Like, what is -15, right? So that's the weighted sum of the color and the size for over here. It came to somewhere near -15. That's where it came from, but what does that mean? How can I interpret it? What I want to know is whether my berries are safe or poisonous, and telling me like -15, like, okay, thanks for that. Not very helpful, okay? So here's what I'm going to do is I'm going to take this and I'm going to apply the function I just showed you, softmax, to it. And here's what it's going to look like, okay? So what we're seeing here is the probability that the berries are safe. Over here, when we're in this region with this particular size color combo, it's saying that the probability of being safe is very close to 1, okay? And then when we're out here in these regions, these particular combos of size and color, we're saying that these ones have basically close to 0 chance of being safe, all right, which we know antecedently corresponds to being poisonous. If there's 0 chance you're safe, then that means you're unsafe, right? So we have taken this previously somewhat uninterpretable, nicely curved, but somewhat uninterpretable plane and bent it into something that now corresponds to a probability distribution, something that we can now interpret, understand, right? I'll just show you for the linear model as the last thing. If we took that, this plane, and bent it here, is what it would look like, right? And here we can see probably even more clearly what the problem is. It's correctly predicting that these two are very likely to be safe. And down here, that's giving it a pretty low probability of being safe for this cluster of berries. But for this one here, it's a huge gap, right? It's saying very confidently that these berries are safe, whereas in fact, these berries are poisonous. So even though it's not a good model, we can still bend it into this more interpretable pattern by applying this softmax function to it. All right, so that's the new content for today. Well, I hope you'll all come back tomorrow. I hope it's enough of a teaser, like where do these weights and biases come from, to come back tomorrow. And at the end tomorrow, we will circle back to language modeling and sort of put the pieces together to at least maybe start building out some kind of conceptual framework as to how models like ChatGPT really work. So thank you all so much.